sequence is a list of numbers, or in our case, an infinite list of numbers. And when we write down a sequence, we either write down an is equal to some formula, usually involving n, or we write down a list. We write a1, comma, a2, comma, a3, a4, etc. And that list goes on forever and ever and ever and ever. All right. So that was our sequence. And then at the very end of class, I started to talk to you about series. So we did some details with sequences where we looked at limits of sequences, and we used some tools such as we used L'Hopital's rule. We used looking at if we had rational formulas for our sequence, then we could look at highest power on the top and the bottom. And we even used the squeeze theorem. And so we were interested in limits of these sequences. And then at the very end of class, I started to talk about section 8.2, which is the topic of, or the introduction to series. And a series is an infinite sum of numbers. So rather than having commas between the numbers that I'm looking at, I might have something like a1 plus a2 plus a3 plus a4. And I have plus signs between every single number. So the most crucial what's the word I'm looking for? The thing that you want to remember to keep these guys separate is that your sequences have commas and your series have plus signs. If you get to the test and you mix that up, you're hosed. So remember, sequences, list of numbers with commas, series, a sum of numbers. All right, I'm going to hold off on questions on sequences today. I'm going to hold off. I'll ask at the beginning of class on Wednesday about any sort of limit questions that you might have about sequences, just because we're going to the computer lab for the second hour, so I want to make sure that we get through the new material that I'd like to get through today. Okay, so last time, I introduced you to an example where we had a ball that was bouncing, and the ball bounced up to a height of 6 feet, and then it came back down. And so we had an axis with time and an axis with height. And so the ball itself is going straight up and straight down and straight up and straight down. The ball is not moving forward in terms of its space. If the ball is moving straight up and straight down, what's moving forward is time. And so the second time the ball went in the air, it went to a height that was 5/6 of the original height. And the next one, the ball went to a maximum height that was 5/6 of the previous height. And so where we left off was that we had, for the ball, we came up with a formula for the total distance traveled. And the total distance traveled by the ball, well, the ball went up to 6 and then came back down. And so we had 6 feet, but we had to multiply that by 2. Okay, because we went up and then we came back down. And then the next time around, the ball went 6 feet, but only 5/6 of that. And so we had 6 times 5/6, and then the ball went up in the air and came back down, so we had to multiply that by 2. And then the next cycle for the ball, we had the previous number, which was 6 times 5/6, and then we multiplied that by 5/6 again, and that was the maximum height of the ball in the next cycle, and it went up and down, so we multiplied by 2. And so let's see, that took care of the first cycle, that was 2 times 6. The second cycle was 2 times 6 times 5/6. The third cycle was 2 times 6 times 5/6 times 5/6. And so our next one, we're going to take this number and multiply it by 5/6 again. So we have 6 times, now we'll have 5 6 raised to the third. And so we have 2 times that number. Are there any questions on where I'm coming up with this formula? Not necessarily why I care about it or anything like that, but where it's coming from. Okay, so if this ball continues to bounce forever and ever and ever and ever, then this sum is going to continue forever and ever and ever. And the way that I indicate that is by putting a plus and then 3 dots. Now at some point our measuring devices won't be able to measure the height the ball is bouncing, but our theoretical ball is going to bounce forever and ever and ever. Okay, so this infinite sum, this is an example of a series. Okay. I have a sum of numbers, it's an infinite sum of numbers. Okay, so the real question is, how far has this ball traveled? Has the ball traveled an infinite distance?
No.
Has the ball traveled a finite distance? What's that?
Limits.
Yeah, so it's not really clear. Will this ball travel an infinite distance as it's bouncing? It's going to go up and down, and then up and down, and up and down.
That never stops bouncing.
And it never stops bouncing. Although at some point, I mean, my finger, which is modeling the ball, is moving at such an insignificant bouncing height that you can't even see it moving. But it never stops bouncing. So here it is. Okay, so our goal is to figure out a way to find the total distance bounced or traveled by the ball. All right, so we cannot add all the terms at once, right? I mean, if we could add all the terms at once, that would mean that we could add an infinite number of numbers, bam, all at once, and that's going to be a problem. So instead what we do is that we look at this sum and we start out with just one term. So I nix the rest of it and I look only at the first term. And then I look at what happens when I add the first and the second term. And then I look at what happens when I add the first, the second, and the third term. And I see kind of what's happening with our pattern. And so we cannot add all the terms at once. So we add the terms one at a time and look for a pattern. All right, so that's what we're going to do. We're going to start out and look just at the first term. And I'm going to call that S1 because it's my sum that just includes my first term. So my first term is 12. 2 times 6. And then I'm going to look at what happens if I add the first term, the 12, plus the second term. Now my second term is 2 times 6 times 5, 6. I'm not going to worry about the fraction part. I'm just going to write it as 12 times 5, 6, and not worry about simplifying it. And then I'm going to look at 3 terms altogether, and then I've got 12 plus 12 times 5 sixths. And then my third term up here looks like 12 times 5 sixths squared. And my fourth sum, S4, is going to be 12 plus 12 times 5 sixths plus 12 times 5 sixths squared plus 12 times 5 sixths to the third. Okay, so I have my first 4 terms. And so each of these what we call partial sums, they're part of that infinite sum over there. These each have a name, and so this first one is called the first partial sum. And the second one is called the second partial sum. And so on. And if I keep going with this, I can eventually come up with a formula for the nth partial sum So if I think about this, let's think about kind of what's happening here. We've got 12 plus 12 times 5, 6, plus 12 times 5, 6 squared, and I'm going to keep going, dot, 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 but I am going to stop. So I'm going to have a stopping term at the very end. My very last term, it's going to have a 12 involved with it. It's going to have a 5, 6. Now 5, 6 is going to be raised to a power. So I might go back and look at my other partial sums that I have up here, my first, my second, my third, and my fourth. And when I look at these, what I notice is that the last term has the 5, 6 raised to a number 1 less than the partial sum that we're looking at. And so this very last one right here is going to be n minus 1. Now, some of you might look at this and say, wow, that's a really long sum, and it sure would be nice if I could write that in a shorter notation. And you might even be saying, oh, I remember looking at long sums before. When did you see long sums before? Anybody remember ever adding up a whole bunch of things? Yeah, when you looked at Riemann sums, and eventually Riemann sums turned into integrals, okay? But before they were integrals, we used this summation notation. And so we can look in shorthand as saying the sum, so we're looking at 12 times 5, 6 raised to some power for each term. The first one, 5, 6, is raised to the 0, and the last one, 5, 6, is raised to the n minus 1. And so we raise to the power of I. Actually, let me take that back. Our I value will go from 1 up to n, and our power will be I minus 1. So think about what happens there. When I is equal to 1, we have 12 times 5, 6 to the 0. That's our first term. When I is equal to 2, we have 12 times 5, 6 to the 2 minus 1, which is raised to the first power. And so on. In the very last one, we plug in n for I, and we get n minus 1 for our power. Okay, so that's our shorthand notation. And this big sigma sign says add up all those terms. Okay. So remember, our goal here is to figure out the total distance traveled by this ball. And the way that we're going to do this is we're going to start by looking at just the first term in the series. And then we're going to look at a number that adds the first 2 terms in the series. That's S2. Then we're going to look at a number that adds the first 3 terms in the series and the first 4 terms in the series. And so what I have created over here, this first guy's a number, this second guy's a number, third guy's a number, fourth guy's a number, this nth guy is just plain a number. I've created a list of numbers. So I've taken this series over here, and I'm analyzing this series by looking at a list of partial sums, a list of numbers. And so to analyze a series, what we're really analyzing is a sequence of partial sums. So the list, S1, S2, S3, dot, 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 is a sequence of partial sums. All right, so I've got a definition for you. All right, so what I'm writing up here is kind of weird, and I totally agree with you that this is kind of weird. We're looking at a sum of numbers, and so we're looking at a series, but instead of looking at this sum of numbers and trying to understand, bam, let me write this down and figure out what its sum is, I'm going to look at a pattern. I'm going to look at first term, first plus second term, first plus second plus third term, and see if I can come up with a pattern. And then I can analyze that list of numbers, that sequence, the list of numbers, the list of partial sums, and see if I can figure out what happens to the limit of this sequence. And that's going to tell me about my sum over there. All right, so here's our definition. if a sequence of partial sums sequence is Sn, if Sn approaches some number s as n goes to infinity, then we say the series converges. Okay, so if I have my series, which looks like the sum of all the AIs, where I goes from 1 to infinity, this is our series, and so we are adding a whole bunch of numbers, A1 plus A2 plus A3 plus A4 plus etc. I'm adding up all these terms, and our partial sum of the series is given by Sn is equal to the sum where I goes from 1 up to n of AI. So our partial sum starts at A1, adds on A2, A3, etc., all the way up to stopping at An. We say our series converges to S if the limit as n goes to infinity of the partial sums is equal to that number S. If the limit as n goes to infinity of our partial sums diverges, then we say our series diverges. All right, so when we want to add up a bunch of numbers, we're starting with the first term, and then we're looking at the first plus the second term, and then the first plus the second plus the third term. And we're seeing what happens to this list. As n goes to infinity, what is happening to this list of terms? If our sequence of partial sums converges to a number, then our series converges. And if our sequence of partial sums does not converge to a number, if our sequence of partial sums diverges, then we say our series diverges. All right, so let's look at our example. In our example, the question is, what happens to our partial sum Sn as n goes to infinity? Okay, so we have a formula for Sn. I just erased it on the board, but hopefully you have it in your notes. Sn was 12 plus 12 times 5/6 plus 12 times 5/6 squared plus dot, 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 and I kept going until I had 12 times 5/6 raised to the n minus 1. And the shortcut way of writing that was the sum where I goes from 1 up to n of 12 times 5/6 raised to the I minus 1. All right, so our goal is going to be to figure out what happens to Sn as n goes to infinity. So our goal is to find the limit as n goes to infinity of this formula right here. Okay, so I've written a lot of theory and a lot of definitions up on the board. Before we continue with our example, which hopefully will clarify things a little bit, are there any questions that you have right now? All right, so let's see if this example helps out a little bit. Okay, so I look at this series that I have right here. This is a finite series because I've stopped. I have not put a plus dot 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 at the very end, so it doesn't go on forever and ever and ever. But this finite series, this partial sum right here, there's a nice pattern going on here. Notice that every term has a 12 in it. And every term has a 5/6 raised to a power. And so this series is of a very special and particular form. It's of the form where I've got a number, an a value, and I have a fraction that is being raised to a power, and that power is increasing on each term, and I call that my r value. And so we have, so this series is of a special form called a geometric series. All right, and so the general form here is Sn is equal to the sum where I goes from 1 up to n of a times r raised to the I minus 1. In our example, a is equal to 12 and r is equal to 5/6. And this is called, the series is a special form called geometric series, and because this is a partial sum, this is a finite geometric series. Right here. And I want to analyze the generic form, the special form here, so that we can use it in 150 different examples rather than just this one specific example that we have here. Okay? So we want to analyze this sum right here, where a in our example is 12, and r in our example is 5/6. So let's look at this thing. And this is a really, really, really good place for you to follow exactly what I'm doing right here. Take it home, explain it to your dog, explain it to your daughter, explain it to your son, explain it to your partner. Whoever will listen to you, what we're going to do is come up with a formula to describe this sum. A nice, compact formula. Okay? So this is a really good place to know this formula. So there is a nicer way to describe this sum where I goes from 1 up to n of a r to the I minus 1. So check this out. All right, our sum, when I is equal to 1, we have a times r to the 0. When I is equal to 2, we have a r raised to the first. And then we have a r squared plus a r to the third plus dot, dot, dot. And I keep going until I hit I is equal to n. And so my very last power here is a r to the n minus 1. Okay. The next thing we're going to do, I'm going to take this equation and multiply everything in this equation by r. So I'm going to multiply the left side by r, and I have r times Sn. Check out what happens on the right side. If I multiply this whole right side by r, what happens to my first power here? instead of being r to the 0, what do I have that raised to now? Yeah, that should be raised to the first power. So I now have AR to the first. And this one, when I multiply by r, I have AR squared. And then I have AR to the third. And AR to the fourth. And my very, very, very last term, instead of being raised to the n minus 1, I'm multiplying that thing by r, and so I now have AR to the n. This is a cute and clever trick that somebody came up with a long time ago, well before I was born. And so we multiply that equation by r. We're now going to subtract. We're going to take the first equation minus the second equation. All right, so I'm going to subtract, which means on the left-hand side of the equation, I have Sn minus r times Sn. And on the right-hand side, this is way cool. All right, I've got AR to the 0. And then AR to the first. Oh, look. I've got an AR to the first down here, and I'm subtracting it off, so these guys are going to cancel. Bam, gone. And I've got an AR squared minus an AR squared. Bam, these guys are gone. And an AR to the thirds, they're gone. What about this AR to the fourth? Will that cancel?
Mm-hmm. Yep.
Yeah, that's stuck in the dots right here. And so AR to the fourth minus the AR to the fourth. And even this last term, AR to the n minus 1, well, there is an AR to the n minus 1 as part of this sum down here. And so these guys are going to cancel. And then this poor little lad down here is left. Okay, AR to the n. So we end up with AR to the 0 minus AR to the n.
Why is it minus?
Because I'm subtracting this entire equation off. So I want to think about distributing this negative sign. So
because they progressively get smaller, it's still larger minus smaller quantity.
yes, that is correct. Well, as long as in our case our r value is 5, 6. If our r value is larger than 1, then it would be different. So, are there any questions on where this equation came from? This little itty bitty equation with 4 terms in it. Okay, so our goal is to find a nicer way to describe this sum. This sum is Sn. So I'd like to solve this equation for Sn. If I want to solve this equation for Sn, the first thing I need to do is isolate Sn so I can factor it out. So I have Sn times 1 minus r is equal to a, r to the 0 is just 1, so I'm not going to write that anymore. A minus AR to the n. And if I want to get Sn completely by itself, what do I need to do next?
Divide.
Yeah, I need to divide. Now, I do need to put an asterisk on this. And the asterisk is that r cannot be equal to 1, otherwise we'd be dividing by 0. And so we end up with Sn is equal to a minus AR to the n over 1 minus r. Okay, so now we have a really pretty and nice formula for our partial sum. So now the question is, what is the limit as n goes to infinity of our sequence of partial sums? So we're looking at the limit as n goes to infinity of Sn. We have a nice formula for Sn. we have a minus ar to the n over 1 minus r. Right, now, one thing I can do here is, if I look at this, we're looking at the limit as n goes to infinity, and so there's some terms in here that don't involve an n, and I can factor them out into the front. So, for example, I can rewrite the top of this as a times 1 minus r to the n over 1 minus r. And the a has nothing to do with n, and the 1 minus r on the bottom has nothing to do with n. So I can factor those in front of the limit symbol. And so I have a over 1 minus r times the limit as n goes to infinity of 1 minus r raised to the n. Okay, so I look at this limit here, and I'm still asking what happens to the limit of our sequence of partial sums, and it all comes down to answering this question right here. This question right here is, as n gets really big, what happens to 1 minus r raised to the n?
Negative infinity eventually.
Well, actually, it depends. It really depends on what this r value is. So if r has a size, and this is a place where size really, really matters. So if r is really, really big, then as you take a big number and you raise it to a power, it's going to get even bigger. It's going to explode. In particular, if the size of r, the absolute value of r, is bigger than 1, then the limit as n goes to infinity of 1 minus r to the n diverges. Oh, that was really sad. That was the last large piece of chalk.
Last lecture mentioned r being between 0 and 1, and of course it's going to get.
Yes, and so if the size of r is less than 1, in other words, if r is between 0 and 1 if it's positive, and between negative 1 and positive 1 if r is possibly negative, if the size of r is less than 1, then the limit as n goes to infinity of 1 minus r to the n, if you take a tiny number and raise it to a really, really big power, then that tiny number raised to a big power is going to be uber tiny. And so this r to the n is going to go to 0, and so we'll have 1 minus 0, which is 1. And so if r is less than 1, then this limit converges. All right, so we have all the tools that we need up here on the board to write down the following theorem. If the size of r is less than 1, then the geometric series given by the sum where I goes from 1 up to infinity of a r to the I minus 1, that sum, which if I write it out looks like a plus a times r plus a r squared plus ar to the third plus ar to the fourth plus dot, 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 goes on forever and ever and ever because my sum is going up to infinity. If the size of r is less than 1, then this geometric series converges, and its sum is sum where I goes from 1 up to n of a r to the I minus 1 is exactly equal to, okay, so if our size is less than 1, size of r is less than 1, then this term right here, the limit as n goes to infinity of 1 minus r to the n, is equal to 1. And so we're left with just the a over 1 minus r. And so if the size of r is less than 1, then this sum is equal to a over 1 minus r. And if the size of r is greater than 1, then the geometric series given by the sum where I goes from 1 up to n of a r to the I minus 1 diverges. Okay, so what I'd like you to do right now is I'd like you to turn to your neighbor and I'd like you to say hello. Series is a sum where we have a common term that can be factored out, an a value, and then the leftover pieces are going to be a 1, an r squared, etc. When we have a series in that form, as long as the size of r is less than 1, then this series is exactly equal to a over 1 minus r. So in our example, we had that our total distance was equal to the sum where I goes from 1 up to infinity of 12 times 5/6 raised to the I minus 1. Now, I'm going to do something here that you may think is a little bit silly, but I think it's a really good practice to get into, and that is that sometimes these subscripts don't exactly match our formula. So our formula here, our standard geometric series has I starting at 1 and going up to infinity, and then the power on the r is I minus 1. And so here I immediately see that, but in some cases this may not be the case, and so I like to write out some terms. And so the terms I would write out, I'd have 12 times 5/6 to the 0, which I'm not even going to write that 5/6 to the 0 because it's just 1, plus 12 times 5/6, plus 12 times 5/6 squared, plus 12 times 5/6 to the third, plus dot, dot, dot. And what I want to be able to do is I want to be able to write this as some number that I can factor out of every single term. In this case, that's a 12. And then what I want to be left with is 1 plus 5/6 plus 5/6 squared plus 5/6 to the third plus dot, dot, dot. So I want to be able to write my series. An alternative way of writing this series up here is a times 1 plus r squared plus r to the third plus dot, dot, dot. And so if I can factor out that a and have a 1 as my first term, and then the r, and then the r squared, and the r cubed, then I know that I have the right form of my series. So once I write it like this, I can identify a few things. This 12, this is my a value. And inside the parentheses, I've got a 1, that's my r to the 0. And then I have r to the first, and so 5/6 is my r value. And so what this theorem tells us, after all of that theoretical work that we've done, this theorem that we just wrote down up here tells us that as long as the size of r, which is the absolute value of 5/6, so the absolute value of r is the absolute value of 5/6, as long as that is less than 1, and is absolute value of 5/6 less than 1?
Mm-hmm.
Sweet. So, yes, so that is checked off. So our series, the sum, where I goes from 1 up to infinity of 12 times 5/6 to the I minus 1 is equal to a over 1 minus r. And our a value is 12. And our r value is 5/6. So this infinite sum is exactly equal to 12 over 1/6. And if I multiply by my reciprocal, I have 12 times 6 over 1, which is 72. So at the end of time, well, really we don't have an end to time, but as time goes off to infinity, this ball has traveled, the ball that started and went up 6 feet and back down, up to 5/6 of that and back down, up to 5/6 of that and then back down, 5/6 of that and then back down. And it kept being smaller and smaller bounces. The total distance traveled by that ball is 72 feet. Totally weird. All right, so let's wrap up with one final example for the day. All right, so let's say we've got 4/5 plus 4 over 25 plus 4 over 125 plus 4 over 625 plus dot, dot, dot. All right, our goal is to figure out what this sum of numbers is equal to, what this series is equal to, if it's equal to anything. All right, so the first thing I want to do is look at this series and say, can I factor anything out? Yeah, I can factor out a 4 on the top, and I can factor out a 5 out of the bottom, so let's go ahead and do that. We have 4/5. And we're left with 1 plus 1/5 plus, 1 over 25 plus 1 over 125 plus dot, dot, dot. All right, so I've got this sum. I factored out a 4/5. So now the question is, are these terms in here? It looks like what we have here maybe is an a value of 4/5. And then I have a 1, which is an r to the 0. And it looks like our r value is going to be 1/5. But just to double check that, is it true that 1 over 25 is that 1/5 squared? It is, and so that works. And 1 over 125, that's 1 over 5 to the 3rd. And so I can rewrite this as 4/5 times 1 plus 1/5 plus 1/5 squared plus 1/5 to the 3rd plus dot, dot, dot. And so I have a geometric series. And on my geometric series, the size of my r is less than 1. My r is 1/5, and 1/5 is definitely less than 1. And so this sum is going to be equal to a over 1 minus r, where a is 4/5 and r is 1/5. Geometric series, r is less than 1, so series converges. And if we can simplify this, then we figured out what the series converges to. So we've got 4/5 divided by 1 minus 1/5, which is 4/5 again. And so I can multiply by my reciprocal, and I end up with a value of 1. Which is totally weird that our geometric series converges to 1. So we add up an infinite number of terms. Those infinite number of terms will add up to a total of 1. All right. Are there any questions or comments about that? All right, so I've given you a lot to think about today. I'd like to give you some practice problems.